In this IBDP portion of the uncertainties, this is very important chapter because this is linking with your IA portion where you have to do the calculations and all these things have to do. Now, what exactly is uncertainty? Now, how it is measured, or what exactly does it mean? That's a very good example over here. That if we take a magnesium ribbon, right? Now, the magnesium ribbon mass, actual mass, the true mass of the magnesium ribbon, suppose is this, right? Having this.
Yeah.
So exactly this mass, right? 0.25,
uh,
846, or 246 and this, right? So,
Yeah.
but we don't have the weighing balances, right? In our
Yeah.
school or in our colleges, right? Why? Because of the inability of the funding. Yes, this might be available in super specific labs such as NASA and all, but we
Yeah.
don't have it at our disposal. So this is a very important question to us, that how can we represent this? So the best way is what? Suppose you have got a particular suppose machine, which digital machine which has got two places of decimal, right? So it'll be measuring what? It'll be measuring 0.26, right? Right? 0.26, right? If it has got three places of decimal to measure, so it'll be 0.258. If it got one places of decimal, so it will measure zero point 0.3. So is this the correct weight, exact weight? No, this is not the exact weight. But are we at fault? Is the student at fault who is measuring? No, he's not at fault, right? So neither these values, any of these values, is actually the true mass of the magnesium ribbon. So this tells us the question that how can we represent the inability of the machine, right? It's out of
Mhm.
control, right? How to
Yeah.
represent inability of the machine? We can represent the inability of the machine by putting uncertainties, by putting the factor of the uncertainty over here, that how much is the machine having uncertainty, right? Isn't it?
Yeah.
So that concept is called as the uncertainty. Now uncertainties, if you see uncertainties can be of two types. One type of uncertainty is called as the random uncertainty. Other is called as the systematic uncertainty, right? Random
Yeah.
uncertainty and systematic uncertainty. What do you mean by random uncertainty and systematic uncertainty? Random uncertainty is a uncertainty which is due to the limitations of the measuring apparatus, which is beyond our control, or due to the other uncontrollable variables which is there. Example, you might be thinking, systematic uncertainty is what? Systematic uncertainty is due to the human error, right? Human error, or
Mhm.
it is due to the faulty experimental setup. I'll be coming one
Yeah.
by one, both of it. Now, if you see up the random uncertainty, see a very good example which is there. Suppose we have taken 20 centimeter cube of the 20 centimeter of the magnesium ribbon. I've
Yeah.
taken 20 centimeter of this magnesium ribbon. What I'm doing, I'm dividing this magnesium ribbon into into 10 parts, right? 10 parts. And equally 2 centimeter, I'm just trying to cut it, right? 2 centimeter, right? Cut it. Now, I'm cutting 2 centimeter. I'm taking a weighing balance and doing very precisely, very, very precisely, very honestly. Now, when I'm doing this, you'll be seeing that the weight, if you see, that the weight will be coming like this: 0.27, 0.28, 0.28, 0.27, 0.26, right? So
Yeah.
these values, if you see, these values are all what? All are 2 centimeter we have precisely cut and putting into the weighing balance, right? Now,
Yeah.
these results which is coming, we are seeing at the first instant what we are seeing. At the first instant, we are seeing that all the readings are not the same, isn't it? They are not the same. All the readings are not the same. So this is due to the random uncertainties. What is random uncertainty? We have cut everything 2 centimeter exact, but it is not exactly same. This is due to the random uncertainty. What is random uncertainty? Random uncertainty is the uncertainty caused by the limitation of the measuring apparatus, right? Which is beyond our control, or other uncontrollable variables. So this is called as a random uncertainties, right? It is due to the limitation of the measuring apparatus or other uncontrollable variables which are inevitable during the experiment. Now, moving to this part, if you see that when we talk about this machine, right, we to also see that this particular machine, if you see, why does it come, right? Suppose the internal, there's a motherboard. which can get heated up, isn't it? Which can get heated up. So it can get heated up, and there's a fan which cools it down. Fine. Suppose you're seeing that the air gush can come, right? Suppose somebody is opening the door, entering, right? Are these are in our control? Please tell me. There's not in control, right? So
Yeah.
this is called a random uncertainty. But random uncertainty, how can you catch that if anything has got a random uncertainty? You'll be seeing that the values which are coming, this is a mean value. Can you see? This is the mean value which are giving. The values which will be coming will be distributed both side of the mean value. Do you get my point? Is it clear to you? So you're seeing that the mean value is how much? So sorry, my bad. 0.27, right? The mean value. You'll be seeing that if you're taking the values, how can you catch that it is a coming under this? Random uncertainty will be having values distributed on both sides of the mean value. Did you get my point? Both sides of the mean value, it will be distributed, right? So this is a very important portion we have to master. That whenever we are seeing the random uncertainty is due to the inability of the machine, limitations of the machine, or due to the other uncontrollable variable, which is inevitable. So over here we have to see that how to represent this uncertainty. We have to represent this uncertainty by what? See so it is weighing this. So it will be 0.27 plus minus 0.01. This is the way we represent the uncertainty part, right? That okay, we are seeing
Yeah.
that this is that. See, can you see this? From the mean value, it is plus zero point 0.1 over here. Can you see this? It's minus zero point 0.1 also, right? Is it clear? So that's a very important information we have to draw, right? Now, next part is that if you see when you talk about when you talk about the this uncertainty, how to find out if you're having an analog instrument, right? Suppose you're having a burette, the random uncertainty will be half of the smallest value. Is it clear?
Okay.
Half of the smallest value. You're having a burette in this, right? We're having a burette.
Yeah.
This burette will be measuring what? This burette will be having what? This is what? This is approximately zero point 0.5, right? Zero point 0.5. Isn't
Uh-huh.
it? So this is very important. So it is half of the smallest value, right? This sorry, this is zero point 0.1, my bad, right? This is how
Okay.
much? 0.1, right?
So
Isn't it?
zero point zero
So
0.05.
it was 0.05 plus minus
Okay.
0.05. This is where we represent. If you're having a digital instrument, right, it will
Uh-huh.
be the smallest division. This is very important. It will be due to the smallest division, which is there, right? This, right? So this is very important that whenever we are seeing the uncertainty from the machine itself, we can find out the uncertainty if it is analog or if it is digital. The smallest division is what? This is zero point zero 0.01, right? So this half of the smallest value, right? So the uncertainty is what? Suppose you are seeing what? Oh, here it will be 0.005. Fine. Understood? Now,
Yeah.
if you add these two uncertainties, right? Suppose you are trying to take, suppose while quoting, you are saying what? While quoting, you'll be saying that the digital instrument will be quoted as plus minus the smallest division, because these two adds up, right? 0.005 plus 0.05, right? You started with zero, right? You started with zero, you teared it. Understood? So just remember this quote if you have got any confusion, that for digital instrument, it is plus minus the smallest division, right? Is it clear to you? Means you started with zero zero tear, right? Plus minus 0.005. Now you weight something. Suppose it's 2.45, right? Plus minus 0.005, right? So if you add these two, what are you getting? You're getting plus 0.01. So if you forget also, if you don't consider this also, so in general, what is the uncertainty? Uncertainty of the measurement will be the will be the smallest division of the digital instrument. Understood?
Yeah.
Now, if you have got a machine which weighs this, can you just guide me that what will be the uncertainty? What is the smallest division this machine can weigh? Please tell me. What is the smallest
Uh,
value this machine can weigh?
zero
Point
point
zero zero
zero
one
zero zero one. Yeah.
one. So it will do plus minus 0.001. Is it clear? So what have we
Yes.
defined? Suppose 2.3137 2 plus minus 0.001. Easy. Easy, na?
Yeah.
Easy. Got it. So this is a very important information we have to process over here, that whenever we are seeing the uncertainty, right? The uncertainty we have to process like this. Got it? Is it clear
Yeah.
to you? So this is a very important information. Next bit is that whenever we are seeing that the word called as precision. Precision is very important part you have to master. Prior
Okay.
going to the precision, let's do the systematic uncertainty. So, what are systematic uncertainty or systematic error? I told you. Systematic uncertainty or systematic error are due to the faulty experimental setup. Experimental setup. One. Or they are due to what? They are due to faulty apparatus, right? I'm showing to you. I'm going showing to you. See, suppose you are trying to measure the amount of enthalpy given out, heat given out, right? Suppose you have
Uh-huh.
taken a solution in a polystyrene cup and put a thermometer inside it. Agreed? Put a thermometer inside it. Now, tell me one thing, that this beaker, if you take like this will be, suppose a reaction you have taken, suppose a displacement reaction you have taken, right? Zinc plus copper sulfate gives you zinc sulfate plus copper, right? You have taken a displacement reaction over here. Understood? Now, if you're taking a displacement reaction, this zinc will be displacing copper, right? And this will be exothermic reaction, and the temperature will rise. Now, if you take this beaker as it is,
Yeah.
will it be trying to stop the heat going out from over here from the glass vessel? It won't, right? So isn't it better that we have to take this glass beaker into another beaker containing glass wool, which will be insulate the system? Did you get my point? Isn't
Yeah.
it? If you take the beaker like this, will you get the exact amount of the temperature rise? What do you feel?
No.
No. Is this a faulty experimental setup I've made? Yes. Did you
Yeah.
get my point, right?
Yeah.
Every time you'll be getting a lower value, isn't it?
Yeah.
Suppose that this,
But it
yeah,
would
yeah, tell me.
it won't be accurate, but it'd be precise all the time.
Yeah, it
Right?
will precise. Very good. Very
Mm.
good. Appreciate. But it will be, see how to catch that this is a systematic error. It'll be, for the systematic error, it's very important that you have got a literature value that will be helping you. Literature value. If you have, suppose the literature value for this zinc plus copper sulfate is, suppose the temperature rise, suppose will be giving you, suppose 15 degrees centigrade, right? Understood? Literature value. For the catching the systematic error, always remember that you have to have a literature value. That will be best, right?
Yeah.
We have to know the literature value. That will be really helpful for us. Did you get my
Uh-huh.
point, right?
Yeah.
So we have to get a literature value where you can compare. So will it give 15 degrees increase? It won't. It will always give you what? It will give you a 13, 12, 12.5. Do you get my point?
Uh-huh. Yeah.
13.5. Is it clear?
Yes.
So the values are distributed one-sided. Can you see this? One-sided, right? 15 should be
Yeah.
the actual value, but the values will be always one-sided. Why it is coming lower? Tell me why the values are coming lower over here. The temperature, because heat is getting lost, right? Lost.
Yeah.
We have not taken this setup in a correct form, right? Where we are taking glass wools and all. We have not taken like this,
Uh-huh.
right? With glass wools and all. We have not taken this, isn't
Yeah.
it? Did you get my point over here? How to do it? Fine. So this is a very important information we have drawn, that whenever we are seeing that in this reaction, right? This will be giving you a faulty experimental setup, and that will be always and always giving you a lower temperature. Always. Is it clear? The
Yeah.
values will be one-sided. So this is due to what? The faulty experimental setup. Now
Okay.
think of this. Yeah, tell me one thing. Yeah, tell me. You're asking
No,
something.
no, no, yeah, I'm just agreeing.
Fine.
Yeah.
This is clear to you. Now
Yeah.
think of this situation. Think of the situation where we have taken. Think of this situation where we have taken, the polystyrene cup, and we've taken the glass full over here, right?
Yeah.
Everything we have done correctly. Now suppose I've added a thermometer which is faulty, suppose,
Okay.
which always is measuring 2 degrees more, right? Got it?
Okay. Yeah.
So 15 degrees centigrade is the temperature we are searching. Suppose
Yeah.
this thermometer is always faulty, a digital thermometer, suppose, right? Is faulty.
Yeah.
It's always measuring 2 degrees more. So the
Yeah.
values will be what? 17, seventeen point
Uh-huh.
five, 17.1, 16.9. Is it clear? See,
Yeah.
one-sided. Again, I'm getting the values. Did you get my point over here, right? We are
Yes.
getting one-sided. So this is very important when I'm asking that. This will be one-sided, right?
Okay.
Systematic errors will be always and always. They will be one-sided of the literature value. There you can catch, right? Understood this part? And why
Uh-huh.
this error has come? Tell me. Due to the wrong experimental setup. No, everything is fine. The experimental setup is good. We take in glass wool. We ensured that. But what happens? Please tell me. The thermometer was wrong. Wrong thermometer we have taken, right? Is it clear? You get my point over here? Fine. Understood this part? Fine.
Yeah.
Yes. Just 1 minute. We talk about. So we learned this part that systematic errors are due to what? Due to the faulty apparatus or wrong experimental setup. And systematic errors can be very well easily judged by what? Very well easily judged by the the literature value. If you are having literature value, will be very important. Now, if you have got the literature value, we can easily find out that what is the amount of the systematic error. So because systematic error, we have to know that how much systematic error is creeping in the experiment. Isn't it? Is it clear
Yeah.
to you? That's very important. That's very vital for us to know that what is the actual amount of the deviation which is happening. Now, to know the actual deviation which is happening, we have to learn what? We have to learn the percentage error. Is it clear? What is the percentage error? Percentage error will be, suppose the literature value is 15 degrees centigrade, right? Now we have used a faulty thermometer which is always showing 2 degrees more, right? So 17.2, 17.5, these values are getting. So can we see that how much amount of the systematic error is there? Because systematic error percentage is very important for us to understand. Why? Because we have to easily correct it and reduce it or eliminate it. Random error will be there, 100% will be there. Due to what? Due to inability of the measuring apparatus or other uncontrollable features. So this is very important that when we want to find out the amount of the deviation or amount of the systematic error, we have to calculate the percentage error. What do you mean by this word called as percentage error? Percentage error will be experimental value minus the accepted value, right? Accepted value is a literature value, right? We are taking, right?
Yeah.
Experimental value means you're having 17.2. Accepted value is 15 degrees centigrade. Divide by 15 degrees centigrade into 100. Do you did you get this point? Is it clear
Yeah.
to you? So as I've told you that systemic error is due to what? Faulty apparatus, or it is due to the wrong experimental setup. Let's try to see now that what are the causes? What are the causes of the systematic error? Examples. Suppose,
Okay.
as I've told you, that beaker is not insulated well. It should be insulated by a glass wool,
Hmm.
and the reaction does not occur instantaneously, or the thermometer does not respond instantaneously. We are not taking a very precise thermometer, right? Understood? Did you get my point? So this is
Yeah.
very important that if you see that, when also the third important is that if the concentration of the sodium hydroxide is less than zero point 0.1, so the measured temperature will lies less than the actual, because concentration is very low. Is it clear? So
Yeah.
systematic errors can be used, can be eliminated by what? What are the ways by which you can eliminate these errors? We can eliminate these errors by changing the way of the experiment. Or we can see the, so we have taken the beaker,
Yep.
changing the way we what? We put it another beaker where we put it the glass wool over there.
Yeah.
That's the way we are trying to change it, right? Is it
Yeah.
clear? So this is very important for us to know, right? Now, moving to the next part, we to see that if we see that when we talked about the systematic error, we talked about all these random errors. We have to now know that what is precision and what is accuracy. To understand precision, what does precision means? Precision means that it is related to the reproducibility of the results. This is very important, right? Now,
Yeah.
if any student, suppose any student is doing that experiment very
Yeah.
precisely, right? That will be giving him the reproducible result also, isn't it? Very important, right? That they are readings which are taking with high precision, right?
Yeah.
When you're doing any sort of experiment with high precision, you'll be seeing
Yeah.
that the values are very close together. This bit you have to understand, right? All the values will
Uh,
be very close together and very close to the mean average value. This part you have to understand this thing, how to catch that it is precise or not. If the values are precise, you'll be seeing that they will be very close together, all the recorded experimental values, and they will be close to the mean average value we are taking. So this is a very important information we have to know, that precision is what? Precision will be dedicated to what? Precision is actually dedicated to the reproducible result, how close they are together, right? So if you see this, that that the that a boy, that a student A, right? Suppose Mr. A and suppose Miss B is taking the experiments, right? So see over here, Mr. A, the values are what? Very close together, see. But Miss B, can you see the values which are coming over here? They're scattered. So we can tell
yeah.
that Mr. A is doing a very precise experiment. Is it
Uh-huh.
clear? and the values will be very close to the average value, where Miss B or Mr. B, these values will be scattered. See, they are not close together. So we can tell
Yeah.
that the first set of readings will be precise, and they will be, the second set of values is not precise.
Yeah.
Fine. Is it clear?
Yeah.
Now this is very important. This is very, very important, that we can, if the values are scattered like this, right?
Yeah.
We can use the standard deviation. This is a very important point I'm discussing. You can use the standard deviation to give an idea of the precision of the set of the measurements we are taking, right? Is it clear?
Okay.
Larger the standard deviation, less precise is the measurement. So this is a very important portion we have to master over here. I'm just putting this off, just 1 minute. So whenever we are seeing that precision,
Mm.
we can see that we can very well get the idea of the precision by what? The standard deviation, right? Larger the standard deviation, less precise the measurement, right? Now
Okay.
we're going to the part of the accuracy. That what do you mean by accuracy, right? This is also very important. What do you mean by accuracy? Now, if you see accuracy, what is accuracy? Accuracy refers to how close a measurement is to the actual value of a particular quantity, right? Isn't it? Fine, isn't it? Suppose we are taking these readings, right? Suppose we are trying to take this readings, right? Here, taking the readings, right? So this is precise, right? This is very precise. This is not agreed. But suppose the literature value is suppose 19.5, right?
Yeah.
So are these value accurate? No, these values are not accurate. What is accuracy? Accuracy refers to how close a measurement is to the actual value of a particular quantity. To get my
Yeah.
point, right? How close is to the actual value of the quantity, right? We're getting. So these
Yes,
values are
I.
precise, agreed, but these values are not accurate. So this is a very important point. So if you see that, now this is a very important information I want to share, that if you see accuracy term is very well linked to the literature value or any recorded value. You can write down recorded value. Suppose in your school, your teacher had done the same experiment. She has done the same experiment and found the temperature 19.5, right? Recorded this temperature very precise. She's expert. She's done this and recorded as 19.5. Now you are doing that experiment, right, over here, like this. So you can compare with this value. If you don't have literature value, there should be a recorded value. And this accuracy will be linked with what? Linked with the systematic error, right? Systematic error, right? Is it clear? Systematic error tells you what? Systematic error tells you that that are due to the errors to the faulty experimental setup or wrong experimental setup we are doing, right? Faulty experimental instruments or wrong experimental setup. So if you're seeing that, if you want to find out the accuracy, how to compare these values? Tell me, but with whom? That are these accurate or not? With whom to compare? We have to have some value, na,
Yeah.
reference value, right? This reference value can be of two types. This is very important. This
Uh-huh.
reference value can be a literature value
Yeah.
from the internet, you can get out from the
Yes.
research papers. Second, a more responsible, suppose skilled, qualified teacher has done the
Yeah.
same experiment earlier and recorded the
Okay.
values in the school notifications, that okay, I'm doing that point 0.1 mole per decimeter cube of, suppose we are taking suppose I've taken NaCl solution. I found out that this is the value which are coming. Do you get my point? At what time the evaporation starts? Suppose they're taking that at what temperature the evaporation starts for NaCl. Here recorded this value. So accuracy is very well linked to what? Accuracy very well linked to the reference value you have got or not. If there is no reference value, how can you compare these values are accurate or not? Will you be able to compare? If there is no reference value, how could you compare? Do you get my point over here? If there is no reference value, we can won't be able to compare it. We talk about. So when we talk about the accuracy,
Yes.
we can very well see that this will be connected with what? This will be leading to a indication. What is the indication? It will tell you that how much systematic error is there. Is it clear? How much systematic is there? If the values which are there, the actual value is what? This book which has been said. So the actual value is what? Suppose actual value is suppose 19.5, right? Isn't it?
Uh-huh.
Actual value is 19.5. but the machine is faulty. No, the machine is not the might be faulty, whatever, but the value is 19.5. But all the values are coming how much? Please tell me. 21.2,
when you
21.3, 20.3,
okay,
right?
yeah.
So we can see that they're one-sided. You can see this one-sided, right? We
Yes.
can very well understand that how much amount of systematic error has cropped or not.
Uh-huh.
The
Yeah.
thermometer might be measuring plus 2 degrees more or 1.5 degrees more, right? Is it clear? The
Yeah.
student is doing very well, right? Is it clear? So this is the portion of this is the portion. See the graph tells you very important thing, right? So this picture. See a lawn tennis suppose trainee player. So always is hitting the ball precisely, right? Isn't it precisely, right? But is it
Yeah.
is it accurate? No, this is not accurate. This is what this should hit over here. So obviously this is a good precision. The player has got good precision but poor
Yeah.
accuracy. Is it clear? Suppose in a
Uh-huh.
cricket match, suppose this is a wicket, right?
Yeah.
And suppose the ball is hitting over here constantly, right? Constantly
Yeah.
he's hitting the ball over here, right? Constantly. So it's
Yeah.
accurate.
Yeah.
But is it, sorry, it is good
It's
precision.
precise.
It's
Yeah.
precise, but is it accurate? No, it's not accurate, right?
Mhm.
Although he's hitting the ball in the same place.
Yeah.
So this is very important, that if you see that when we when we talk about this is finally very important. What the difference between accuracy and this precision? Precision refers to the reproducibility result, where accuracy refers how close the values are to the true value of
Yeah.
the measurement. This is very important to know, right? This What is the
So
difference?
accuracy and reliability would be the same as well.
Yeah, yeah,
Okay.
fine. Is it
Yeah.
clear? So now going to this part, if you see that whenever we are seeing the random errors and systematic errors, we know, right? Is it clear? Now coming to this part, when you're quoting, this is a very important information. When you're quoting the values with uncertainties, right? It's
Uh,
very important for you to know that how to quote the values, how to quote exactly, what to quote. Now, if you see, when we talk about the quotation, right? That's very important for us to know that when we quote these values, it will be very important that we have to know that how much uncertainty we have taken. See, you have taken point 0.1, so we should not tell these. Understood? We should not tell this. We should refer to as point 0.1 plus minus point 0.1. Is it clear? So while quoting this, you'll see that uncertainty is usually quoted one significant figure, right? But
uh,
yes. Suppose depending upon, see, point 0.1 over here. Uncertainty is usually quoted one significant figure. So the measurement also should be stated in the uncertainty of the last significant figures, right? Is it clear?
uh-huh.
Get my point? So best example is this. If you're taking this point 0.2, it'll be what? It'll be this, right? 1. Do you get my point? You have to quote like this, right?
Wait.
Fine. See,
Wait.
we are taking this, see, this. So,
Yeah.
so over here, see, we have to cross this
Uh-huh.
then.
Although
How
we
do you
should
get?
only have
Yeah.
one decimal place because it has one
Yeah,
decimal.
yeah, yeah. Means better to take the significant figures for the uncertainties. One significant figures, it makes the
Uh-huh.
makes the decimal points, you can tell, right? Also, that'll better. So how many
Yeah.
decimal places? There are four
Or
decimal places. So we have to tell of this, right?
yeah.
So this is a very important for us to understand that actually whenever we are quoting also, this will be very important for the IA part. This is very important for the IA part. IA part, this will be tested, and also paper number 1B, that will also test it. So please try to
Hmm.
memorize this part, that this part I'm just sending this part to you. So thank you. So
Yeah.
this was all about what? This was all about the random uncertainties and the systematic uncertainties and the precision, and and these particular in the next part we'll be also learning that how to calculate the uncertainties. That part will be going in the next video. Right? Thank you so much.